Hey, this video is made to using this example to explain how we solve internal loading problem. This is quite a good example because it has not only show how do we solve internal loadings, and it also have some distributed load to throw in there. So now let's take a look. We learned previously how internal loading is made of three aspects: normal, force, and shear, V, and bending moment. And we also learned their positive sign convention. So we're going to use this knowledge to solve this problem. And for this problem, they want you to find internal loading at point C. So in that case, they want you to find normal, NV, shear, and bending moment, all three of them. Okay. So how do we solve this? The first approach is going to cut it. If they want you to find at point C, we go ahead and cut at point C. So when you make this cut, you have left section and right section. Either one will work. So we might, at this video, demonstrate both of those two different sections to show we actually get the same results. Okay, so if we go with, let's see, if we go with the right section, okay, if we decided to go with this right section over here. Okay, so we're going to draw our FBD for the right side. What do we have? We'll have this beam, and we also have this is what we cut, right? What forces do we have on there? We'll have this distributed load to where we are. So we'll have all those forces going downward. Okay, but here's some question for you to think. Do you know exactly what's going to be the intensity right here, which is this point? Do you know the intensity there? Okay, that's something you want to figure out, right? Then let's go back to this FBD, right? So you have this distributed load. Any other forces? Well, point A is fixed support, but it's at the left section. So for the right, B is free hanging. There's nothing on there. So we have only distributed load. But remember, you have to, this external force, which is for this problem, distributed load, have to be balanced by what? Internal loadings. So what's the internal loading here? That's where you cut. We're going to use our rules. It's normal, shear, and moment. Normal, to make a positive, have to be what? Tension. So to make this tension, it's on this side. We have to be pulling to the left to make it in tension, to make it elongated. So that's our N. So for our V, shear, it's going to be parallel to the cut, so it's going to be up and down. And to make this section to go turn clockwise, that's the sign convention to make a shear, that have to be going upward. So that's our V. Well, for the bending moment, to make this happy smile, at this side, you have to bend like that, right? So that's our NVM. So this is critical. You're going to have to get the arrows right, and so that helps us to get the internal loading sign convention right. Now we have that. We can go ahead and try to solve those three unknowns. This is a 2D equilibrium problem, right? Like we learned in statics. For 2D, you can solve three unknowns, and so we can definitely solve them. Now let's do this. Forces at x direction. What do we have? We only have n to the left, so that's going to be negative. No other forces are x direction, that be equal to 0. What do we get? Normal force equal to 0. You solve the first of the three. Now let's look at the y direction. Forces are y. Well, we have a shear, force V, that's going upward, so it's positive. And then you have distributed load going downward. Well, but do we know exactly what is the intensity right here? Right? That's what we need to solve. What's the intensity right here? I know you already kind of know, right? You're going to use similar triangle or proportionality to figure it out. So how do we do so? So here we can go ahead to copy down this entire beam. Entire beam, base is 9 meter. The height is 270 Newton per meter. Then we'll have at point C. And that's what you're solving right here. And at this point C, this length is 6 meter. So how do we solve this? We're going to use proportionality. So here we're going to set up the equations. So for this small triangle, the base is 6 meter. However, for this big triangle, the entire base is 9, right? So over 9. And then you are trying to solve this question mark. What's the intensity right there? And that's the height. And here for the big triangle, the height is 270. So from here, you can calculate the intensity where you cut will be 270 times 6 divided by 9. That will give us 180. And the unit is Newton per meter. Okay, so knowing that, we can actually write it down here. So that's 180 Newton per meter. So we're going to go back to our forces at y direction. So you have all the forces going downward. And what will be the concentrated load? So BC length is 6 meter. So what's the equivalency? Equivalency will be the triangle area will be half base times height. That will give us 540. Is that correct? 540 Newton. And where is this located? That's going to be at the center of this triangle. So that's going to be 1/3 from the fat end. So we'll be right here. That's how much? 2 meter away from point C. Okay. Okay, so knowing that, we're going to go back to our force at the y direction. The shear is going upward, and this equivalent of this concentrated load is 540 going downward, so it's going to be minus 540 equal to 0. Then what do we get? The shear is 540 Newton. So now we found both normal and shear force, and we're going to look at our last unknown, which is bending moment. So the rule of thumb is whenever we want to solve bending moment, we're always going to do moment about where we cut, the point where we cut. For this problem will be this at point C. Why do we choose to work on the moment about where we cut? Because normal force and shear force both go through that point, right? So they will not show up in the equation. Therefore, if you do moment about where you cut, the only unknown will be this bending moment you are trying to solve, right? So now let's write down this equation. So moment equation, and first one, this moment is happen to be what direction? Let's see. This is what? This is going to be the clockwise direction, so that would be negative m. And then for this distributed load, you find the equivalent as 540, and it's located 2 meters away from C. C is where you cut, so the moment of arm is 2, and its clockwise rotation is minus. And there's nothing at point B because it's overhand beam, so that equals 0. That will give us our moment as how much? Negative 1080. And the unit is Newton meter as the moment. So when we get an answer as a negative for moment for internal loading, what does that mean? Which means our assumption earlier, this beam is going to be make a happy smile bending like here, but however, the actual bending here is actually the opposite direction. You know, it's exactly the opposite direction. All right, that's the example for internal loading. Well, have a good day. See you next time.